Hello, everyone. Thanks for joining us. My name is Raphael, and today I would like to introduce our speaker, Yanshuai Cao. So a little about his bio. Yanshuai Cao is a senior research lead at Borealis AI, conducting R&D and building products for RBC. Currently, his research spans natural language processing, generative models, and adversarial machine learning. His long-term research goal is to create machines that can learn to reason and adapt quickly from as little data as possible. Yanshuai received his Ph.D. in computer science from the Department of Computer Science at the University of Toronto, and he was advised by Professor David Jeffrey and Aaron Hertzmann. His abstract today, and for today, he will be talking about applications beyond fine-tuning, pre-trained models when labeled data is scarce. In this talk, Yanshuai will discuss cross-domain text-to-SQL semantic parsing for natural language database interfaces as a case study. It will cover several topics: how to encode prior knowledge in model architecture, how to train deep transformers on small data sets, how to and not to perform data augmentation for NLP, and leverage task-specific unlabelled data. With that, I will transfer the stage over to Yanshuai. Yanshuai, please take it over.
Thank you. Thank you for the intro. With this interface, I can't see the audience. Thank you everyone for attending today. This will be the outline of the talk. A quick disclaimer is I originally was a little bit confused about the duration of the talk, so I planned a talk that's slightly somewhat longer than the original allocated 30 minutes. So I might go over time a little bit toward the end. And this is the outline of the talk. So the focus is using cross-database semantic parsing as an example to look at really this problem of hard problem and small data. And there are a lot of tools available for tackling small data problems, ranging from very simple, just ensembling to reduce variance, to weak supervision with things like Snorkel. There are a lot of great resources on these topics out there. I will focus on what's perhaps slightly less known or slightly, problem dependent in this talk. In particular, these 4 aspects. And the talk will be a combination of the survey of prior works, mostly for the first part, and a survey of related work, as well as our own recent work at ACL this year for the latter 3 topics. Okay, before I continue, these are my wonderful collaborators. These are the researchers. These are the engineers who contribute to the demo for the ACL demo paper and the current active demo. And these are the academic advisors who contributed to one of the paper writing. So before we dive further, why do we care about small data problem in this age of big data? Well, whenever you are building a new system, whenever you're trying to bootstrap a product or business, at the beginning, you're inevitably almost always faced with a small data problem before you can enter this positive reinforcing loop of data flywheel. And if the initial thing that you build doesn't meet certain accuracy for certain usability threshold, you can't actually create a positive feedback. So this problem is actually quite common in my opinion. Another way this can show up is if your data created by a user doesn't implicitly give you labels. Somehow you have to label them, with experts' effort. And if you can label them very cheaply by user interaction or cross-sourcing, then this will be very problematic. And the cost of that labeling will be high, and so you will likely end up with a slightly small data problem. So the problem we'll be looking at today is cross-domain text-to-SQL semantic parsing. One potential application of this is in natural language database interface. where we hope to allow users to ask questions in natural language like this, give it to a machine translate that to a SQL query, execute against database, get the answer, and return the answer back to user. The semantic parsing part just means translating a natural language utterance to a meaning representation. Here, the meaning representation will be the SQL programming language. And cross database means we want to train on some database schema and generalize to new unseen schema, because the correct SQL query depends on the database schema itself. So this is a zero-shot cross-database generalization problem. And the reason why this is important is because you don't want to, if you build a natural language database interface, you don't want to just limit to whatever database that you trained for. You want to work on new database. A new domain is just slightly harder variant of that, where a domain could actually tell new entities, not just same entities, same domain, but a slightly different schema structure. All right, so first let me address the elephant in the room. So you might probably all seen the OpenAI Codex, with all the amazing demos, and trained on code from GitHub, and it can perform. If you give a natural language prompt, it can auto-complete your code and solving fairly hard problems in a lot of the cases. So why is this a small data problem? Well, it turns out, comparing to things like Python and Java and JavaScript, there aren't a lot of SQL examples. And in particular, there aren't a lot of SQL example paired with database schema. The correct output really depends on schema. So if you just have the SQL alone, it's the problem is actually confounded. And for security reasons, people don't tend to upload their schema online. So. And in fact, we had a similar work in similar spirit at the ACL this year, which actually came out and was published before the Codex paper that explored a similar idea. Basically, performing code generation, leveraging monolingual data, monolingual Python data that can be found online. We used Stack Overflow data, much smaller scale, obviously, comparing to what OpenAI was able to do, but we had similar findings and using different architecture. All right, so why is this a hard problem? So let's look at the first dataset size. If you look at the size of dataset for the de facto standard benchmark on this task of cross-domain semantic parsing, it's minuscule comparing to some of the other problem. For example, this is neural machine translation, this is QA, and this is ImageNet. The spider dataset size doesn't even show up on this plot. In fact, it only has slightly over 10,000 questions and over 5,000 queries, less than 5,000 during training. What's even worse is this is spread over 200 databases, covering 138 domains. So that's less, about 50 per domain and 25 unique queries per each database. And what's even worse is these databases are not simple, not just simple single table select, like in some of the other SQL datasets. There are about 5 tables and 27 columns in each one, and close to 9 foreign key relations. And furthermore, we need to perform zero-shot cross-domain generalization, meaning we need to train on this 146 training databases, generalize to questions on the development set and test set. These are the development datasets. The one with a subscript means there's a network 2, for example, that's likely in the training. So the domain has the same, but has a different schema structure in the development set. And these are domains that is most likely not observed during training. And another reason why this is hard is a small mistake in the program will lead to execution results being wrong, most likely. And so this is really very different from machine translation, where you make a small mistake, people can still read and make sense of it. If we don't assume the user is a developer and is able to edit the look at the SQL and try to edit it. If we want to do this for non-technical users. And another reason why this is hard is the output is highly structured. So we want to predict a full query that can be very flexible. It's not just a simple intent classification plus slot filling. That is very limiting, because if the intent is not in one of the prepared intents, then you can't actually answer that. By doing compositional semantic parsing, you're not really bound by that. But the output can have nested conditions, subqueries, multiple joins, etc. And finally, in order to make the correct parse, the model actually needs to be able to reason. The reason is SQL is really underspecified given natural language. As I alluded to earlier, it really depends on the schema. For the same natural language question, if the schema is different, the query will be different. So the model will have to take into account the structure of the schema and try to make the correct inference. And one way this could happen is in this simple example. The first line here is the example question: what's the average age in each shop? And here is a very simplified version of some of the schema columns. And the edge here shows some very simple surface level lexicon evidence. The model can look at this, say, oh, the age column age should be relevant here, and the table shop should probably be relevant. But without looking at the schema, it won't be able to produce the correct query, because likely we'll try to do a cross join, which doesn't make sense in this context. The model will have to follow the links provided by foreign key and say the only way to make a correct parse that makes sense is to bring in a third table here. And so this ability to bring in information that's not present in the surface evidence of the questions is very important. Another way SQL is underspecified in this problem is common sense. So, for example, someone asked this question: more than one employee under 25. Under 25 refers to age of employee, but age is not explicitly mentioned here. So the model will have to either leverage knowledge from pre-training or somehow be able to infer that this refers to age and make the correct inference. Another example is domain knowledge, quite similar to common sense, but a little bit even longer tail in terms of knowledge that has to be used. For example, show me the papers after birth. We all know what that means, but for a machine who doesn't really doesn't have the domain knowledge, what does the papers after birth mean, right? It actually refers to publication date of papers that are after the publication date of a paper referring to birth. And these papers should probably be related somehow, depending on the schema of the structure. You do want to, you want them to be in the same topic, for example. And these incredible amount of domain knowledge that has to be brought in, it really requires the model to have domain knowledge in order to do this correctly. And yet the question itself is really short. And that's the problem with this task. When humans speak, there's tons of ambiguity. But in order to make the correct SQL parse, there has to be no ambiguity at all. So in order to fill all the gap in information, model really has to understand structure, have domain knowledge, common sense, and use reasoning to infer what is not there. And finally, the output is structured. It has to respect the SQL syntax and logic. All right, so that's the why this problem is hard. So I'll talk about different aspects of the solution. First, inductive bias. design for structure and reasoning. This part will mostly be a review of things in the literature. So for why inductive bias design at all? Michael Brownstein gave a really amazing talk at iClear earlier this year. If you haven't heard about it, listen to it. It's highly, highly recommended. Probably one of the best science talk ever. He in the talk he advocated for the importance of model exploiting the structure of the underlying space and show that you can learn very robustly and sample efficiently if you do it right, and that's for structure. Another reason why it's important to have good inductive bias design for the problem is for reasoning. In this work in iClear last year, the author proposed this notion of algorithmic alignment and how it's important for neural net that tries to perform reasoning tasks. They showed three example problems: summary statistics, relational argmax, and dynamic programming. And they show that different neural architecture can or cannot learn on these problems in a sample efficient way because they have different algorithmic alignment with the underlying algorithm that can solve the problem. At the core of it, the intuition is really simple, actually. The intuition is this: if you have an algorithm that can solve the problem efficiently, for example, Bellman-Ford algorithms for solving an instance of dynamic programming, and if you have a neural net that in structure resembles this algorithm, meaning that for example, you have the loop here that corresponds to the looping structure here, and then you only have a neural net at the inner loop that tries to replicate the computation at the inner loop of this algorithm, then your neural net can actually learn to perform the reasoning task in a very sample efficient fashion. Otherwise, if you try to do the whole thing with, for example, MLP, then there's no hope to do it with a fair amount of sample, and it will not generalize very well. So that's the intuition. Given this, how we might want to model the reasoning task and model the structure in this problem? Well, we have seen that there's a lot of structure provided by the schema, the foreign key links in the schema, for example, and there's obvious links provided by surface level lexicon evidence, like partial match of cities, employee, etc. So does that mean that we want to model this with a graph neural net? Well, that certainly is capturing a lot of the structure here, but it's not capturing everything, because although the token don't have direct link here and between the words in the question, there might be actually, it might actually provide context depending on the meaning of the words in the questions and schema. So we can't rule out all the other potential links. So really, this is not just a graph. This is a multi-graph. Between every two words in the questions, in the schema, and across the question schema, there's potential link that needs to be modeled. And beyond that, there might be additional links that are colored as shown earlier. So really, this is a multi-graph. If you look at this, and this suggests that one should use a transformer in conjunction with a graph neural net, perhaps. But it turns out, graph transformers themselves are really graph neural nets, and the correct connection might be obvious, and you might have heard about these connections. And this blog post talks about in detail how it's connected. So I will skip the details here, but just take my word for it for now. So now that we know transformers are essentially graphs, what's interesting is we can modify transformer additionally to account for these special edges. So we don't actually need to use transformer in conjunction with graph neural net. We can use what's called relational aware transformer, which are a small modification on top of transformer, and it's basically a multi-graph neural net in a sense. And the trick is to add additional terms here correspond to the links that we saw, the explicit links that are here. So here we have a red edge here. We'd add a term with its own embedding corresponding to this, and with a link here, we'd add another term corresponding to the yellow link here, and same for this. You might wonder where the links come from. Well, the schema, the foreign key link is known from the schema structure, and this is all dependent on the questions and the schema itself. And you can do a little bit of pre-processing before you run the neural net to use a bunch of heuristics to find what are the potential links. And it's okay if the heuristic is noisy through the transformer, for the computation. As we saw the connection to graph neural net earlier, it's actually really doing reasoning. It has a chance of filling in what was missed by the heuristics, and also remove some of the noisy edge if the heuristic got it wrong. So that's for the input. On the output, how one might do it, how to make sure that output structure is respecting SQL grammar. One way to do this is using the TrainX framework. And the idea is, instead of producing the surface tokens of SQL directly, we want to predict the SQL AST instead. And in order to produce this hierarchical tree object, we cast the tree into a sequence of tree constructing action steps. And the neural net just predict this sequential sequence of tree constructing actions. So in the end, you still get to use a simple LSTM to predict this sequence of actions, but with a grammar that guides this action sequence, with a grammar telling what is the legal set of actions to take at each step. This is bound to produce a grammatically correct tree. And you can get even further performance improvement by not using just a flat LSTM, but using what's called a parent feeding tree LSTM. And all it does is at each step, instead of considering just the hidden state of the previous node, you'd also give it hidden state of some node that's before it that correspond to the parent in the abstract syntax tree. And that gives a better inductive bias for the decoder. So putting it all together, a common framework of architecture that's used by a lot of work in this space looks like this: a graph to tree transaction model, essentially. And this is also the architecture that we use in our ACL work. And we used a Roberta encoder and relational aware transformer from this RAS SQL paper, which introduced the relational aware transformer for this problem. And on output we have parent feeding LSTM and TrainX. So does all this inductive bias design really help? We can look at the progress on the spider benchmark leaderboard. Here we're showing the exact test match accuracy on the vertical axis, and on the horizontal axis the date. Red star is the state of art at any given time, and the baseline is attention seek to seek. Basically, you see if there's no inductive bias built into the model, it's really poor. It doesn't do much at all. And this is trying to bake in some knowledge of SQL syntax into the neural network decoder. Not quite the TrainX I talked about earlier, but similar in spirit. This is same model plus data augmentation. And this is using an intermediate representation that try to bridge the gap between natural language and SQL, basically building more inductive bias into the output side. And with BERT, same model without BERT. Incidentally, right at the 50% mark here is roughly separates the model that use BERT or doesn't use BERT. I think that's pure coincidence. And then we have this work, RAS SQL, that introduced this relational aware transformer, and that gave a very significant performance boost. And work that tries to take this idea, but instead of using a BERT encoder, they use the encoder from BERT, but further fine-tune auxiliary tasks that are specific to semantic parsing. So task-specific pre-training of the encoder give some performance gain. And this is our work that basically showed that you don't actually need this task-specific fine-tuning if you can just train more transformer layers in the stable fashion, solve the optimization problem better, basically. And you can get pretty remarkable performance boost. And finally, the most recent state-of-art entry added some further, inductive bias modification to the to how you model the graph. And if we look at this, the first idea for modeling the schema as a graph came out right here, but it wasn't really performing very well because it was just modeling schema as a graph. And from relation where transformers, everyone started to model both the question and schema jointly, and also use database content as one of the heuristics for linking, finding these initial links. And this all gave a very substantial gain. All right, so that's for inductive bias design. And next, I'll talk about the training with these architectures. So, with all that inductive bias, if you can't train it, it's really no good. From a optimization perspective, the model really, looks something like this. There's a number of fresh transformer layers that are initialized and needs to be trained. And then there's some pre-transformer module. This actually could be a pre-trained model like BERT, but because the model is already initialized and you tend to use a smaller learning rate for them, for optimization, this is really different from these fresh transformer layers. And then you have a bunch of layers like a Trios TM that are really stable for optimization. So this is a general type of architecture that will show up if you want to, use pre-trained model coupled with new, transformers, relation transformers, and variants to solve these hard problems on small data with, some ability for understanding structure and reasoning. And can we actually train this? People, tend to believe that for training deep transformers, you need large data sets. But is that really true? Well, transformer training itself is unstable. And the reason is, and the common techniques required for training transformer in a stable fashion is you need large batch size, layer normalization, and learning rate warm-up. You really need all three of them. But on a small data set, you can't really use large batch size because then you'll be close to doing batch gradient descent. So that will hurt your generalization performance. And some previous work have also found that layer normalization is actually hurtful for both the performance model and its generalization. And the reason is it shrinks the gradient size by this factor. And this causes high variance of the optimization at the beginning of the stage of the optimization. And this shrinkage, coupled with the root mean square normalization of Adam, introduces oscillation at the beginning of optimization. And this keeps oscillating until optimization stabilized, but at that time, your model tends to get into a bad region already. So they show that you really want to get rid of layer norm. And if you initialize the model in the right way, the training can still be stable. And the key is to scale the input and these parameters by a factor proportional to this depth of the transformer with this polynomial power. But this is not really, applicable to our situation because the method assumes that the input embedding to the whole network can be randomly initialized, and you can control the norm of that thing. And also, it only applies to vanilla transformer. But we have to use a pre-trained because we need to leverage the knowledge from pre-training. So we are in a situation where small data set requires that we can't use large batch size, and small data set requires that we have to use pre-trained model. So what do we do? Inspired by the previous work, tfixup, we derived that this other method. It turns out you can scale this parameter v and w by a factor proportional n to the minus one half, different factor from previous one, and also dependent on this scale of the input. So you do a forward prop through the training data set on your pre-trained bird, for example, aggregate this statistics and make it part of your scaling factor. And for relational Weyl transformer, it's somewhat similar. And you just scale this factor here. How does this work? Well, with increase in depth, if you don't do it, it just completely collapses. It doesn't lead to any gain, and model performs very poorly. But with the DT fixup, initial training is stable, and you get consistent gain with increased depth. And recall that with more depth, the transformer is like a graph neural net, and so it's increasing the ability of the model to perform reasoning. The axis scale here is not comparable between these two plots. So this bar here is really corresponding to this bar here. So we get performance boost. And if we look at the increase, it's actually helping across the board on all different questions of different levels of difficulty. But we get extra, additional, boost in the extra hard category. All right, so basically this method shows that you really don't, although large data set helps, but it's not a hard requirement. It's possible to train deep transformer on small data set, and the inductive bias in transformer itself can lead to better generalization. And next part, I'll go a little bit quick. So data augmentation. So this will be a quick survey of some of the previous work, as well as this work in progress of ours, which will come out soon. So there's actually a very good survey on data augmentation for natural language processing. If you're interested, you should definitely check out this paper. Has method for all different aspects of all different problems in NLP. I'll just focus on the methods for semantic parsing. The method for text classification really doesn't apply here, because if you randomly replace word with synonyms or drop words, you tend to change the meaning. So you can't use simple methods like that. One of the very influential paper in this space is synthesizing data with asynchronous grammar from this building a semantic parser overnight paper. And it allows you to bootstrap the data set from no data at all. If you can do it right, it gives high precision, high coverage, but it's very, very labor intensive. And for non-computational linguists, it's very hard to get this right. I tried to do this myself. We were able to do it, but it was a lot of work. So I will not dive into details of how you do it, but just say this for non-computational linguists in the audience, this is pretty hard to do. And if you try to get to a data set that has very high compositionality, you end up with generation utterances that are not very natural, and it's very hard to fix that with cross-sourcing. And a method that slightly easier to do is to induce asynchronous grammar from existing training set rather than handcrafting that from just expertise. And the good thing is it's still high precision, but it's lower coverage with this grammar induction, and it's still somewhat hard to do. So not very recommended, and I'll not dive into details to do, unless you are a computational linguist, in which case this should actually not be a problem at all. And there's this method called good enough compositional data augmentation. This is very simple to implement, provides medium precision, medium coverage, but it's a little bit noisy, and the follow-up work showed that it's not the best. There are a better way to do it. One such method is learning to synthesis. The idea here is instead of trying to induce synchronous grammar that gives you SQL and utterance in parallel at the same time, you just try to induce grammar for SQL, and then you learn a translation model that maps the SQL to utterance. And the translation model, depending on the training data, might or might not be super good, but they show that you can get this to work. This is akin to back translation idea from machine translation. And there's other work that have very similar idea as well. Gives good precision, good coverage, not super hard to implement, but you still have to induce this grammar for SQL. Our current work shows that you can make this even simpler if you go in the opposite direction. The idea is we don't want to synthesize SQL first. We want to go from schema to column to utterance and then to SQL. And this is very easy to implement despite this complex pipeline, because every single step along the way it's actually training a neural net. So for non-computational linguists, it's actually fairly friendly. So the idea is we want to train a model that predicts, given the schema, try to predict the column list. So this can be your existing training data, like the spider across many domains. And that this can work across domain because it's conditioned on the schema. And then conditioned on the columns, you can fine-tune a T5 model to generate questions. And this brings in a lot of knowledge of large-scale pre-training, gives you very coherent, very high-quality questions. And then you pair this, use your a parser that you train, a teacher parser to give you SQL, and pair that with the questions and give to a student model as the augmented data, just like in the previous learning to synthesis, but in the opposite direction. And when we do the synthesize, we perform beam search through the T5 generator and use the teacher parser to filter out any questions that are paraphrases. So basically, we want to keep questions where whenever the SQL changes, and throw away questions that are paraphrases. And we show that this actually is very important for getting a good performance boost. The idea is we want to, basically reduce the spurious correlation that might exist between SQL sketch and across SQL sketch and between SQL sketch and database columns, etc. We don't want to paraphrase this. And here's how it works. This is prior work, and on top of our DT fix up, we showed a pretty substantial improvement. 2 point at this stage is pretty substantial on this data set. And we also use previous augmentation on our baseline. The improvement is much less, not very significant. And this is also consistent across the different level of difficulties of questions. And one reason why this works is you can see that not only it increases the dataset size, it also brings down the normalized mutual information between the database, the tables and the SQL sketch, and the columns and the SQL sketch. So if there's any spurious correlation that's in the original data, it helps reduce that. And here are some examples. You can see that I can generate very simple questions to very complex one with subqueries. Okay, last very quickly, we said this problem has this property that partial utility, you can't get partial utility from partial correctness. So can we change that a little bit? So a solution beyond machine learning is to try to benefit from the top K accuracy instead of the top 1 accuracy. So when you predict a SQL, the output decoder, you can perform beam search, and that gives you multiple hypotheses. And the top 5 in the beam have much higher accuracy, chance of capturing the correct prediction than relying on the top 1 being correct. That's as expected. But how can you leverage that? One way we propose that is build an interface that show multiple hypotheses and explain the SQL to user. Not use neural language generation, but use a mechanical, we use a grammar that produce mechanical language, basically language that are a little bit terse, but it's very controllable and it's deterministic, and we can highlight the difference between the hypotheses. And so the idea is a user can then quickly spot how each of the hypotheses differ and judge for themselves which one corresponds to their intuition. And a demo with a better interface is at this link here. All right, with that, that's the end of my talk. Thank you very much.
That was an excellent talk. Yeah, definitely a lot of work that you guys have done for sure.
Thank you.
I'm amazed. That's excellent. So to questions, I think there's a question on here. There's one question here by IK Okoro. And his question is, how do you account for the differences between train and dev like network 1 and network 2? I don't know if that question is clear enough, but this question was asked towards the beginning. So I'm going to assume it was towards the beginning of the presentation. Maybe that might give a better pointer.
Yeah, I don't know if the person is still in the audience. Maybe you want to clarify the question.
Correct. That's true. Yeah.
I didn't get it. Network 1 and network 2?
Network 2. Anyways, yeah, no, the person is not. Anyways, I do have a few questions myself too, because this is actually very interesting work. So how does the model, or the entire model itself, how does it adapt to a new database or a new schema?
Right. So as I showed earlier, the input to the encoder contains both the question and the schema. Right? So it's a part of the input. So if you go to a new domain, you just give the schema, and the model has learned, basically take a questions and reason with the information in the schema, tries to draw the correct inference to some degree. But obviously, the accuracy that we see on this dataset is just around 70 in exact match. So yeah, I wouldn't say it's being able to do zero-shot generalization, and solve the problem.
Yeah. Okay. Makes sense. And then one last question also. I mean, how does the latency of the entire, so if I were to run this on I'm going to assume it's probably going to require some form of like GPU architecture for inference. How does it perform? How is the performance of the algorithm on maybe just a standard GPU accelerator versus on the high-end GPU accelerator?
I would say we have a demo online. I mean, there if many people try to hit at the same time, there might be other issue beyond the GPU. But like if you just like when we just have like our own testing, the compute itself is not a big problem. Like the latency very, very low, and there's no significant delay. I forgot the number. Like what I think we try to arrange like to make it within 20 milliseconds overall, or 30. 200 milliseconds,
200, okay,
or 300 milliseconds overall.
Okay.
I don't know if it's still that number. Yeah.
Got it. Okay, so the IKO Okoro, the person that asked the first question, so he's replied back here. He said earlier at the beginning when you showed us the breakdown of the relatively small data set with about 146 columns in the training set, you show some columns differ in train and dev with some underscores.
Yeah, right. So basically, I mentioned this two notion of cross database generalization and cross domain generalization. Sometimes we use that a little bit interchangeably, but they are slightly different. Cross domain means we are in a domain that the model was never seen, like you will have entities, the concepts that were not trained for previously, and the model only sees the new entity and concept through the new schema. It sees as dev or test time. But sometimes you can have the same domain, but with a different database schema structure. And so similar concepts entity will show up. And that's the left side of the column, like with the subscript, car1 or etc. I hope that answers the question. And yeah, so we don't do anything special to differentiate between these two, cases. The model learns to just generalize. Interestingly, like at least for our model, generalization to database, like this car1, car2, like databases in the domain that has seen before but different structure, on average is actually slightly lower, if I remember correctly. So I think there was some amount of overfitting to the structure. Certainly is still happening.
Got it. And then I think there's also another question here from Max Raphael Sabrosa Marquez. I say the question is, are there some studies in meta learning for this task? I'm assuming he's asking about the small data task that you highlighted toward the end. So he's asking for studies in meta learning that might be able to actually address the issue of having small data.
Sorry, can you repeat the question, or can you point me where I can read the question myself? If I can read.
Yeah, sure. So it's actually the last question. If you go to the questions tab, so the question is, there are some studies in meta learning for this task. That's the question.
The question is there any study of meta learning, or the person is saying there is some meta learning?
I think that's probably there is some meta learning. I think might probably be some of the question.
Yeah,
I can't speak for the person, but yeah.
Yeah, I think that's right. I've seen a paper try to basically cast this meta learning. This as meta learning paper, the meta learning problem, and intuitively that makes a lot of sense, right? You want to your model to learn to basically learn to take into account the fact that you are trying to generalize to a new schema that's not never seen before, and using things like MAML or or all the amazing work along that line. In fact, we've tried to do this ourselves, but we didn't get it to work. At least using MAML and I think Reptile, like one of the follow-up to work to MAML, we didn't get to work. But I know there's at least one paper that got it to work.
Got it. Okay, and then another question just came in. This is probably the last one, hopefully. Do you ever take the raw database values into account?
Good question. Yes, in our work and in a lot of the work following the relational weighted transformer, the RAS-SQL paper, do that. And the way people tend to do that is to consider that you have a pick list of value of the columns that you're considering. And if the question at the beginning, when you try to find these special links, this step called the schema linking, to give you this heuristic initial edges. If you see a text span that have evidence that correspond to what might be in the database content or the pick list of values in the column, then you add a special edge for it, and that gives a very substantial boost because sometimes you don't mention the column explicitly, but these values tell you the column is present. Yeah, and that's an excellent question. And I think Spider dataset collection protocol is such that you get benefit from there, but not as much as you should. Like I think originally RAS-SQL had maybe 3-4 point improvement from just doing this. But if you do questions like in the wild, like how people ask questions, I think you get much bigger boost because people are much more likely to omit, not mention the column name, very explicitly. And doing this is very important.
Got it. Awesome. I think that's all the questions here. Thank you so much for the talk. It was really interesting, really nice, really motivating. And thank you so much to everybody that joined us for to listen to his presentation. Thanks, Yanshuai.
Thank you, Raphael, for moderating, and thank you everyone for attending and staying with me for over the time. Thanks.